Thanks. Yeah, thanks for having me. So today I'm going to talk a bit about kind of one method that I see for using machine learning for actually discovering things. So kind of discovering new physical concepts. So just to preface this, what I really want from machine learning, I want an AI scientist. I want machine learning to be able to accelerate all areas of scientific research. But I think part of the issue with this is that a lot of machine learning research is driven by computer vision and natural language processing and the benchmarks that come out of those. And that's kind of motivated by industry interests, attempts to reach human level performance on these small vision or language tasks. But I think that I think a lot of kind of the easiest applications of machine learning to science kind of take these computer vision or natural language processing approaches and kind of replace the data sets. But I think this kind of misses the point. I think what we should really do is, instead of vision or language, we want AI to reach human level performance at doing research in the natural sciences. And so if we think about that, we kind of work back from it. So natural science, so doing research in the science, it's not a regression problem. It's not a classification problem. It needs understanding. This is kind of the difference. So the approach I like to take, is this muted? Okay. The approach I like to take is that I want to use machine learning to discover concepts and represent them in human language. So the traditional approach to, I guess, just science in general is that you have some data set, maybe it's a low dimensional description of some complex phenomenon. You try to develop theories that describe that data set, maybe make new predictions and test those. But I think the issue with machine learning here is that the history of science has kind of been, so if you look back at like Kepler's third law, this was the motivator for Newton's law of gravitation to kind of explain that, right? Like, we understand Kepler's third law and we try to explain it with theory. Planck's law was actually, this was another empirical equation that was mostly fit to data, and this would partially require quantum mechanics to explain it. But if I have like knowledge wrapped up in this neural net, it's like there's not much I can do with it, right? Like, I can't use the representations learned by my network to kind of drive theory development. So what I think is a really interesting approach that I'm going to talk about today is, so rather than this traditional approach, I don't know, can people see this? It's a bit dim. Okay, I'll just point. So machine learning, you can kind of think of it as like a compression problem. So neural networks compress data. And I think you can get really interesting things out of neural networks on high dimensional data sets. They kind of learn to compress data in new ways. And when you stare at the internal dynamics of the neural network, and I'll show this, it kind of gives you a new way of finding new approaches to science. So rather than kind of building theories that describe the data directly, what I'm going to argue today is that we can build theories that describe the compression of a neural network. So I'll discuss this a bit more. By the way, I'm happy to take questions throughout. So just, yeah. Okay, so the key point is that neural networks trained on big data sets, you have a very flexible deep model, you train it on a big data set, they can find new insights just from seeing all that data and kind of finding all patterns. The issue is it's hard to distill those insights into our language and actually use those learned insights to find a physical insight. So, okay, so outline, we're going to talk a bit about interpretability, symbolic regression, and then we'll talk about using symbolic regression to interpret models. So the traditional strategy of interpretability typically involves feature importance. So this is like a saliency map for a classifier So if you interrogate the output of the classifier and you see what part of the image is it most sensitive to, it gives you this kind of mapping. So it says, okay, I'm looking at the dog's face maybe, or I'm looking at the lion's face. But I think that, yeah, this is another fun example. So if I'm trying to explain the classification of this image of a dog playing a guitar, you can kind of like break it down into like, okay, if I interrogate the description as an electric guitar, this is what the network would be looking at, acoustic guitar or Labrador. But I think that like we don't really need to take this approach. I think we can take an approach of using the scientific language that we already have, which is mathematics. So like computer vision, we don't really have good like theory for describing an image of a cat maybe, but we do for science, right? So this is the language of science that I think we should try to distill our models into. So, I mean, you could just look at any physics cheat sheet. So many descriptions of physical systems are in this simple mathematical language. And I think when we interpret models, we should try to interpret them in this existing language of mathematical expressions. So I'm just going to skip over this. So like, okay, you might ask, okay, like why isn't it that a neural network is perhaps like why can't we just train a neural network and just expect it to generalize far out of distribution? Like why is this mathematical language such a good prior over the space of models? So I think you can kind of look at this as priors over the space of functions. So if you think about these operators, like on this sheet, if you think about all the operators like multiplication, division, addition, these all have geometrical interpretations, right? So like plus is like translation, multiplication is like going from length to area to volume. These have geometrical properties. And so when you distill a model into this language, it actually picks up kind of some geometrical intuition. So this is another reason you'd want to do this. So the way we're going to attack this is with this technique called symbolic regression. So this is a machine learning task where rather than fitting parameters in some huge flexible model, you're going to search over the space of expressions. So maybe you represent an equation by a tree, and then you manipulate this tree and kind of swap in nodes. Maybe you perturb the constant until it fits a data set or whatever other objective you have. So symbolic regression, it's an approach of exploring the space of equations, basically, in a, I guess, directed way. So the state-of-the-art method is genetic algorithms. So recently there's been some approaches that use transformers, but I think the space of equations is just so massive, you have to kind of rely on these symbolic methods. So genetic algorithms are the current best approach to this. They work by basically simulating evolution. So if you think of this as like the genetic code of some equation, you can think of like crossovers. So you mutate an operator, maybe you perturb a constant. You can even do crossbreeding. You can breed two expressions. And this gives you a way of sharing kind of common sub-expressions, maybe. So these are all different ways to explore the space of equations to kind of optimize some objective. So okay, how can you do this? So I have two tools if you're interested. So there's symbolicregression.jl and PySer. These are tools for doing this task of symbolic regression. So they are both genetic algorithms, and they search over equations to optimize some problem. If you're interested in this research direction, there's also these backends that I wrote. So if you want to write your own symbolic regression algorithm, you could rely on this. And this is kind of the high performance primitives, if you're interested. So the way PySer and symbolic regression work, they're a multi-population evolutionary algorithm. Basically, I have a population of expressions. So maybe like 100 expressions. I randomly sample this. So maybe I pick 2 expressions out. Okay, I take those 2 random expressions. I look at the fitness of each. So maybe I look at the accuracy in some random batch of data, and I look at the complexity of the expression. That gives me a fitness. I then take the fittest expression from that random sample, and I create a new generation. So I maybe do a mutation or a crossover or simplification, or maybe I even optimize the constants in kind of like an optimization loop. So these are all different perturbations you can use. After that, you would traditionally kind of replace the oldest expression. So whatever expression has been in your population longest, you kick it out and you put in this new expression. And basically you just go through this loop. Like it's not really that sophisticated, right? Like you just go through this loop enough times, and you basically like simulate evolution, and it gives you a way of finding expressions to optimize the fitness. And I mean, it's kind of like sad in some way. This is still the best method there is. Like, it's such a simple method. Like, there's no large language models or anything crazy. It's just this loop, right? So Peiser does a couple other things that let you exploit parallelism. So one of them is it actually treats each population as kind of like an island. So it's like a species of equation is basically like living on different islands, and they evolve independently. Because they evolve independently, you can exploit parallelism. So it's like one population per core. After some amount of evolutions, you have this migration step, and they kind of go back and forth. So the best equations from the, I don't know, the exponential island will move to the polynomial island, and that will kind of increase the diversity of different populations. So this is a video I spent way too long on, so I'm going to play it multiple times. So this is basically the dynamics of this process. We're trying to optimize that relationship, like trying to overlap those. We go through different steps. We do different mutations. We kind of add a node at the top, optimize the constant. I'm going to play it again. So we start with this, add a node. Maybe we see all the different mutations that are available, add another node, explore the space again. And so this happens in many different populations all simultaneously with crossovers. Like, it doesn't show everything, but basically using this, you can optimize expressions. So I'll just show like a little demo. So this is the Julia side, but it just wait till I get to the search itself. So I'm going to create some processes. This is like my loss function. So the nice part about these frameworks is it's very configurable. You can have a custom loss function, custom operators, custom definition of complexity. So I'm going to define my model. So I'm going to use plus multiplication minus division. I'm going to use this many processors. I'm going to use these different hyperparameters. And basically what I'm doing here is I'm going to search for an equation that describes housing prices. So this is the Ames housing data set. And I'm going to try to find an equation that predicts housing price as a function of the different variables. So like square footage, etc. Okay, so I start the fit. It's going to warm up, compile everything. And then once it starts, it's basically gives you this output. So this is the best equation at each complexity. So this is like the loss. This is some combined accuracy complexity metric. And these are the actual expressions. So you can see like it's kind of heavily correlated with the square footage plus the garage area. But the point is like this is very interpretable. This is in the language we're used to of simple mathematics. So I mean, there's no physical theory of housing prices, obviously, but you can see the kind of, it lets you find new relations just by having these interpretable expressions. And again, like the objective is completely user defined, doesn't need to be differentiable. So you can do things like optimizing the derivatives of this expression against something. You can do symbolic manipulations. You can check if the expression conserves energy or something. Yeah, so I'm going to let it run a bit. Maybe I'm going to skip forward. See. So yeah, so at the very end, I look at this expression. So this is kind of the best expression that balances accuracy, complexity. Yeah, so that's how it works. And there is a Python API. So if you like scikit-learn, you can use this. It still lets you write custom loss functions. You just pass like a snippet of Julia code there, and custom operators as well. Okay. So now to the main point, like, okay, you could use this directly on the data, but I think the far more interesting thing is to use these packages on a neural network to interpret the kind of physics the neural network has learned. I think that's a really exciting direction. So the methodology for this is if I train a neural network on some problem, so I have some neural network trained it on, I don't know, like it's a, I don't know, maybe it's a part of my graph neural network or something crazy. I train it and then I stop training and I freeze the parameters. Okay, I stop training. Yeah.
I was wondering, for sure you have some regularization during this genetic algorithm. I was wondering what's the intuition, because you could just go in arbitrary complexity in whatever polynomials and it would overfit. So
yeah, so there's a few different metrics that are available. So one is called parsimony. That is just a multiplicative factor on the complexity of the expression. So all these concepts are user defined. The default complexity is you just count the number of nodes in the tree. That's complexity. But you could assign different operators different complexities if you want. You could give constants a higher complexity. You can even give it like non-integer complexities if you want. Given that, it takes the complexity and it multiplies it against some parsimony factor. And that's basically how it regularizes it. There's a few other techniques. So there's this kind of adaptive parsimony that looks at the distribution of complexities and it tries to make it flat. So it tries to have like one expression at each complexity. And I find that helps a lot too. Does that answer?
Yeah, thank you.
Okay, cool. All right. Yeah, so, okay, you train the neural network normally, you freeze the parameters. Then what you do is you want to see, okay, like what dynamics has this model actually learned? So you're going to feed in different inputs. Training data set. Test. Okay. Yeah, so you record the inputs, outputs, this network over the training set. And then, so at the very end, you take those inputs and outputs and you fit different equations to it. So you try to find like, okay, this equation, maybe it approximates this relationship between these latent spaces. So it approximates this part of my network, maybe. So the full strategy is you would have some deeper model with multiple layers, multiple kind of sub networks. And what you do with these is, okay, maybe you interpret it as like the first network learns summary statistics and the second network maybe does something with those. So we're going to interpret the first network. We get these two equations as a decent fit to that network. Then we replace that network with those equations. There's a question over there. So we replace that network with the equation. Then what we do is we retrain the second network to kind of pick up any errors, because like it's not a perfect approximation. So we retrain it, and then we fit that one after. Yeah.
So is that split always obvious in the sense that you train your network and you get some expression out?
No. So this is like the trickiest part of this method is the inductive bias needs to be kind of user imposed. So normally what you would have is, let me see if I have one. So normally what you could have is like a summation in the latent space. So maybe it's like a deep set and you sum over particles maybe in that latent space. And then there's a clear separation between what each network is doing. If it's just like one big network, it's a lot harder to interpret each part of it because they could kind of be like inverting the other one and kind of like cancel each other out. And there's a huge functional degeneracy there. So you need to impose some kind of inductive bias to split it. That inductive bias, you kind of need some understanding of like how you want the equation to look, because that will end up in your equation. I mean, one thing you could do is have different types of pools maybe, and kind of see which one works the best if you don't know the good inductive bias. Where you could like sparsify the latent space and see if there's anything that comes out of it. I mean, it's very kind of iterative in this sense. Okay. So the approach that I think is really interesting is to take a neural network that has kind of learned some very accurate relationship on my data, and I treat this as a compression. So it's kind of learned a new way of compressing this data and finding patterns that I didn't know. And I want to distill this into theory. I want to understand, okay, like what is the physical dynamics of this network? And I think that's a really interesting approach. And I think like given the success of deep learning, where you can get much more accuracy than traditional models, I think it's really interesting to kind of see, okay, like what new theories are hiding inside that network that I can try to pull out. So I'll talk about a couple examples. So we had this paper in 2020 where we trained this graph network on just simple particle data. So we have like maybe 5 particles. We impose some force law. We train a neural network on it to predict the dynamics. Then we want to see, okay, what physics did this network learn? So it got very good accuracy. So it probably learned some representation of that physics. So maybe now we can apply symbolic regression and try to pull it out. So let me skip to this one. So we start off, we generate a bunch of simulations, right? So this is just a spring law, generate a bunch of different simulations of particles. We learn to predict these dynamics with a graph network. Okay, so so that we try to get the colored particles and the gray particles to match. Then what we do, and this is kind of the inductive bias that we take, we want that latent space in the network to be simple, so it's easier to understand. So we regularize the latent space to be sparse. And this basically says there's only 2 equations that matter in the latent space. So then what we can do, I'm going to skip this. Then what we can do is actually like run symbolic regression on that latent space and get the force law out. So, I mean, like obviously we knew the force law, but that's just like we're just trying to match, trying to see if it works. But like we could have not known this force law and extracted it from the network. I mean, like we still have to impose this inductive bias, but question?
Not wanting to play devil's advocate, but okay, so put yourself in a situation where you don't know the force law.
Yeah.
Like how much trust do you put into that stuff? That's kind of...
Yeah, I mean, like luckily you can verify all these things, right? Like if you completely distill it to an equation and the equation is terrible describing the data, then you haven't succeeded. Likewise, you could think about, okay, like if you're optimizing sparsity in the latent space and you just can't find a sparse model that works, then that tells you that inductive bias is not the best choice. So, I mean, yeah, it really depends, but luckily you can test any model that you find on the data.
I mean, I wanted to understand this, like how flexible is the system? Because right here, like you're forcing a graph, right? And you're forcing kind of like radial forces, right?
No, so it does get, so we don't impose rotational symmetry here.
So for example, if you had a tensor force, right? Something that would like you would be able to learn that out of this.
Yeah, I mean, you would have like more equation components. So here we don't actually tell it the dimensionality of the force. So you see it actually starts off as this, it starts off as a 100-dimensional force law. So this vector, which is the latent space, is actually 100 dimensions. And we impose like an L1 regularization penalty. And so the network tries to make it as sparse as possible while still fitting it accurately. And so it kind of discovers the dimensionality there. So I think it would work for your example.
I mean,
It depends on the complexity of the law
so
too.
the other thing, like kind of related, is I mean, this also assumes a fully connected graph, right?
Yeah,
Yeah. So like, what if you were to like partially connect the graph?
yeah.
Right?
So I do have an example of that.
All right.
But yeah, I mean, like if you're trying to discover that and you impose the wrong inductive bias, like I don't think it would work. You kind of want to let your inductive bias has to include the true model at the end of the day. Like if you impose that it's not this inductive bias, it can't. I mean, neural networks are good at cheating, so like it could find it, but maybe it would be hard to interpret.
Okay. Thanks.
Okay. So one thing we did is, so we have this dark matter simulation. It's a bunch of dark matter halos. And what we did was we don't really, I mean, we want to find an empirical effective law that kind of describes the clustering here. So we want to be able to predict the overdensity at the center of each dark matter halo using some of the neighbors. So we do a radius cut and we only connect to nearby halos. So that like a halo is like a blob of dark matter so we give it features like the total mass of this blob, the density, and so on. And so what we were able to do is use the same framework to find this law. I mean, it's not really like a law because it's not a perfect fit. It kind of tells you this is strongly correlated with the overdensity of the center halo when you aggregate this equation over the neighboring halos. I mean, this isn't like, it's not really like physically exciting, but it is cool that like we're able to look at this graph network and get physical laws out of it that we can start to interrogate. So like we were able to look at the bottom term, and it was kind of, we realized it was kind of informed by the way we were smoothing the distribution, which is cool. And it's hard to get that kind of information out of a network. Yeah. I don't have much time, so I'm going to skip through these. Yeah, one thing we did is like I mean, this is another example where we know the law, but we kind of, actually, I'll just skip this example. We could talk about it later maybe. But we basically for this data set, we had the solar system data, and we tried to find Newton's law of gravity from the solar system data without telling it the masses of planets. So basically it has to learn the mass of the planets and the force law at the same time, which is another level of difficulty. What we found is that the network was actually like learning a modified theory of gravity. But like once you imply the simplicity constraint, then it learns the corrected masses. Yeah, but I can talk about it later. I mean, some masses are bad, like Hyperion, which is a moon, and Phoebe. It kind of overestimates those masses, but it seemed to work overall. So that was interesting because we don't give it properties of the system, so it simultaneously has to find the properties and the law that describes their interaction. Oh yeah, I'll mention this. So this was an exciting paper led by Ho-Fung Tsui, where basically rather than using this symbolic regression as a way of interpretation, this paper used it as a way of compressing a neural network onto an FPGA. So what you do is you consider the complexity of an operator not as like some kind of intuitive simplicity measure, but you actually consider it the number of clock cycles on the FPGA. So you're trying to find an accurate approximation that is also very few clock cycles. So we get like 90% accuracy, and it gets like a 5 nanosecond inference time on the FPGA, which is really cool. It's cool that you're able to use this in other ways of kind of distilling a network into a symbolic form. Yeah, so I have like a list of papers on the PICER documentation with other cool examples of this kind of idea. Yeah, I mean, so I can stop here for questions. I have like some discussion points that would be interesting to chat about. So one thing I'm interested in is a pure neural network approach to AI for for physics, like no interpretation, is that possible? Like, can we just use neural networks, just train them on big enough data sets and kind of just run with that? Is that even a possible direction? Or do you need to get theory to get out of distribution generalization? Like GR was derived from only a few ideas, right? And it can predict black holes. I feel like neural networks, like it just doesn't seem you can reach that level of generalization of theory. Yeah. Okay, so I'll stop there. Happy to take questions. Yeah. Thanks.
Oh, great talk. So I just had a naive question. It seems that most of the systems that have been tried with this framework are ones that come from an underlying equation. Is there any value in trying to use this on some tasks where we have no hope of finding an equation, like let's say image classification?
Oh, I mean, like, so the one example is like, so the dark matter example, like we didn't know that equation beforehand. And it was kind of lucky. So we applied the same sparsification idea, like try to sparsify the latent space, and it gave us one. Like it gave us one feature that you sum over the surrounding neighbors, but it could have had like 100. It chose to have a single component in that sum, which was interesting. But like we did impose the summation inductive bias, and it could have been that that was the wrong inductive bias, and maybe there's a better law somewhere in there.
So my question was about the cool like searching video that you had.
Oh, yeah.
The question I had was that since it's in Julia, is it using like multiple threading?
Yeah, so there's a few different parallelism backends. You can use multi-threading or multi-processing.
Okay.
The multi-processing is really good if you're on like a cluster and you want to have different population across some cluster. So it works like for thousands of cores. You can scale up and it will have a process on each core. But there is like a multi-threading backend as well.
I see. So and like a slight follow-up question I had there was that, so since we're doing multiple threading, is there a way to like record like stop signals on these threads so that I can like actually see how long it took for like one path? Is there a way to do that?
Oh, by stop signals.
Like I just want to see how long it how long it takes to go into like one branch and then just like
Oh, I see. Yeah, so there is a recorder option that will record like every single mutation that happens.
I see.
Every single generation. It's slower because it's like recording a lot more information. But it does record every single thing that happens. And you could kind of look at that and you can actually see like the family tree of an expression, which is cool. It is like, it's a bit depressing to look at the family tree because it's like so redundant, but you just make it fast and it works. Yeah.
Yeah, I had a question about the evolutionary algorithm. So because the search space is so large, have you found cases where it doesn't find a good expression?
Yeah.
And also like how much does it depend on like different hyperparameters that you give to the algorithm?
Yeah, that's a great question. So yeah, it does strongly depend on hyperparameters. Like, for example, if you choose like a sine and a cosine, it will kind of explode the search space because it has two redundant operators. Like it's combinatorially related to the size of the search space. So for very complex expressions, like maybe over 60 complexity, so 60 nodes in the tree, I feel like that is where you cannot assume that it's found the correct expression. For smaller ones than that, you should be able to with enough cores. So like if you do your search for long enough, you should be able to eventually find it. Yeah. But I think for like more complex expressions, it's good to take this distillation idea, because what it essentially does is like neural networks are very good at learning very complex models. So you could think of this as the neural network is factorizing it into subproblems. And then each subproblem is a simple expression that you can find. And then after you've kind of distilled them, you can compose those expressions and find a much more complex model then so like rather than having to search for this expression, which is fairly complex, you search for these simpler expressions and then stick them together. Of course, like there's other problems with that, but it's a way to beat the scaling.
So just, I guess this is going to be slightly related question. So how do you, like on the dark matter slide, for instance, you have this sum. How is that sum represented in the tree? Is that like a single node, or is it like a whole, does it go all the way down? And
So that summation is from the choice of pooling operator in the graph network. So in the graph network, you compute some node representation, and then you compute like some edge representation, then you do a sum pool, and you use that sum pool to make a prediction. So it's a one-layer graph neural network, and that summation comes from your choice of pooling. So the genetic algorithm did not find that operator, that was imposed by us in the search.
And then like relatedly, what happens if, something has a very, very simple expression, maybe in differential form,
Yeah.
but like the integral sucks.
Yeah.
So how do you deal with that kind of situation? Like
Yeah.
you don't know.
Yeah, that's a great question. So Ben Wanda and I were working with someone who's actually working on that like exact question. So hopefully, yeah, we can do that.
I'll keep an
But yeah, I think like some problems, like if you think about the Bessel function, very simple form in an integral, but like it's an infinite form in if you just try to find it with polynomial.
Hi. Okay, my question's about, so like one of the motivations was the sort of extrapolation, right? Because neural networks just fit and then stop.
Yeah.
But if you're fitting something like sine, it might catch the pattern forever. So
yeah, exactly.
So how well did that work in your?
Yeah. So
experiment?
I actually deleted the slide, but there was another slide after this where we showed that the original graph network, you train with a mass cutoff of the halos. So you don't train on the heaviest halos. And so you distill this network into this equation. Then you test the graph network and the equation on heavier halos. And the equation like destroys the graph network. Like it gets much better generalization. I mean, like it's very problem dependent. Some problems for some choices of operators, it's going to be a good prior. And some problems you're going to pick like the wrong expression or the wrong operators, and it's going to throw off the model. It's kind of like a way of, okay, when you train a neural network, it assumes some prior over the space of models. So like theoretical work has shown that, okay, it's kind of like a Gaussian process with wide enough network. That is a choice over the space of functions. When you translate the network into an expression, you're kind of moving it to a different prior. And that prior for physical problems, it might be a better choice than just a Gaussian process. It's kind of like a different way to think about priors because you're thinking about my model is likely represented by simple expressions rather than this highly parameterized network.
Yeah, thank you. Very, very nice. I guess just a curiosity if, obviously, some of this depends on how you set up the, the operators, right? Trees and so on. We all know the, nice things about prefix notations and other notations. Have you played around with different representations, coding?
Of the trees?
Yeah.
Yeah. So I haven't, but there are many approaches to that. So there's some interesting ideas. So there's one called equation learner, which is essentially you actually choose the operators, it's the activation functions in a network, in a neural network, and you do sparse training of the neural network. And it's actually like equal to the equation. It doesn't work that well in practice because there's a lot of numerical instabilities in this. Like you're basically optimizing the entire equation at once. So it's really hard to use that. Genetic algorithms have always kind of been the best approach to this problem for like the past 15 years. So I kind of just went with that. But I think there's like linear models, which are interesting. There's some approaches that kind of represent an equation as updating registers. And that's a way of kind of sharing sub expressions because you could like say, okay, y equals X plus Z, and then I'm going to take Y and do something else with it. So that, yeah, there's different approaches that are interesting. I've never used them.
Okay, yeah, so on the transformers effectively, can you comment a little bit on why you think, one is working better than the other? What are advantages of genetic versus transformers?
Yeah, yeah, so I mean, yeah, I think this is really interesting because what we've seen, so the group that submitted the large language model to there's an annual symbolic regression competition. All the top models are genetic algorithms. So I think starting in 2022, there was large language models basically submitted to this competition. So Facebook had one that was trained on this cluster of GPUs for like weeks. And you just randomly generate expressions and you try to get the transformer to predict that expression. It just did not really work well on the competition equations. I think it's just like the space of all possible equations is so vast. It's actually a harder problem than language for a transformer to model it. Like you switch one operator and you just get a completely different data set. So it's really hard to model this with like in kind of a neural representation. It's just the space is so massive. You need a symbolic model to approach it. It's kind of like you remember AlphaGo from DeepMind? Like that is mixed symbolic plus neural network, because if you tried to just train a single neural network to predict all possible Go moves, it would just be too massive a space to search. And there's other points like I don't know if you've tried this, but if you ask GPT-4 to add 2 3-digit numbers, it often fails. So it's like they oftentimes just don't have the right like inductive bias for doing math sometimes, or kind of these logical questions. Yeah.
Is there a scheme to kind of mix like a machine learning training with the symbolic, like in the sense of making conditional variables? So for example, like the formula you have there, Rij, you make conditioned on some 20 inputs or something, and it's a neural net.
Yeah. Oh, you mean like
high level symbolic and low level neural net, right? Like for example, x2 is a variable, is a function, a neural net.
Yeah.
Right.
Yeah. So like the output of F is a neural net, and then you find another equation that uses that. Is that kind of what you mean?
No, like you learn high level the symbolic representation, but the low level input variables are actually like factorized neural nets. Like x2, or in the formula above, right, you have cosine x2 minus 2.1 x3.
Yeah, those
x2 and x3 are functions, right? Like neural nets.
Yeah, I mean, I guess so. What I'm kind of saying is like in the second network, when you regress this, Y1 is a neural network. If that's what you mean.
Yeah, I mean, I was wondering if you can symbolically learn with like a neural network under the like training.
I see.
Yeah, like if there's a way to kind of do a mixed symbolic and neural network training, where you like factorize, you find this, like it's maybe a longer discussion, but like I was wondering if you had thought about this.
Yeah, I mean, so one approach that I think is interesting is like, I don't know, like it'd be cool to see if you can. Yeah, I don't know. Yeah, it's definitely worth like an offline discussion.
Yeah.
I think it's like really interesting. Other ways you can kind of interface with neural nets.
I think that's the perfect time to thank our speaker again.